Hello and welcome to my lab. Today I want to fire up this old argon laser. It's really an old beast. Argon lasers are really not used anymore, and this unit also has been sitting still for quite some time. It's Lexel 85 and it should be able to output about 1 watt multi-line, or if you select single laser lines, somewhere between 45 and 400 milliwatts, depending on which line you select. Because as we'll see later, there's a prism selector on the back. Now, the reason argon lasers are not very popular anymore is because of their low efficiency. Because even with this 1 watt multi-line output, this laser requires several kilowatts on the input. So that's an efficiency well below 0.1%, and that's well, not very convenient to work with. It's a very good water heater, and these have been phased out in favor of solid state lasers, which require a lot less power on the input, are more stable, and yeah, easier in operation. Now this unit requires a single phase 32 amps, and the reason it has been sitting still in my lab is because only recently I got access to 3-phase power, and with the help of a transformer I can step that down to a single phase 32 amps, which is what this unit requires. But first, let's have a look around the unit and inside the unit and see what we have. Now the laser has this massive 63 amp 5-pin plug, and it's quite overkill because if you read on the back of the laser, it only can draw a maximum of 32 amp on a single phase. Now I have a transformer to supply that current. It is a 3-phase transformer, but it has a 4-pin socket, and that matches the other argon lasers that I have, but at the moment it's a bit inconvenient. So my plan is to put a single phase 32 amp plug on the laser and the matching wall socket on the transformer, of course with a appropriate circuit breaker. Now you do need a circuit breaker that can trip on both phases, since I'm drawing the power from in between 2 phases. The wiring is done. Got the circuit breaker in there, and now I have a single phase socket next to a 3-phase socket, and I already wired up and plugged in the laser. This is the back of the power supply, which you see a lot of connections. The big one is for the laser head. That of course carries the power to the laser tube, the cathode, and stuff like interlocks, emission indicators. And of course there are water cooling connections, and the power supply itself is also water cooled. It also generates quite a lot of heat, and it has to be carried away. And you also see the connections of the water cooling that run to the head. Now as it turns out, the water cooling connections actually fit the standard garden hose adapters, which is quite convenient because then I can just hook it up to a garden hose. I'll be cooling it using running tap water because that's very easy to set up. I don't have a chiller that's big enough to cool away 7 kilowatts, so getting the hot water cooled and recirculating it is quite a lot of effort, and I won't be running the laser very long anyway, so for the time that I run it, it's fine to just use tap water and discard the hot water. Let's have a look inside the laser power supply. Of course, it is interlocked, so that you can't run the laser with the cover off unless you defeat the interlock. Now the line voltage comes in here, behind the acrylic with the big warning label. There are some fuses in there and a very big contactor that only is energized if the interlock is okay. Over here you see a bunch of test points if you want to check how your laser is doing. At the back here is I think just a generic transformer which supplies the voltage for the control circuitry, which you can find here at the front. Now, the mains voltage is rectified and then filtered by this big inductor and capacitor to generate a DC voltage. That DC voltage is then passed to the pass bank, which is a big array of transistors which regulate the current that runs through the laser tube. And the orange transformer over here is the filament transformer. This one generates a few volts at a very high current for the filament. At the back here is the flow switch, which makes sure that the laser only can run if there is sufficient cooling water flow. Here we're looking at the back of the laser head, where we see the cavity adjustments and the wavelength selector, where we select a laser line. And with these two knobs we can adjust the cavity mirror such that the cavity is well aligned. But with this knob we can also cycle through all the different laser lines. I've taken the cover of the laser head, so now we can have a look what's inside. So let's start at the front. First thing you notice, there's an interlock switch on the head, so I won't be able to turn it on now, but I have it unplugged just to be sure that there are no voltages inside. This is the starter. It has a very big warning sign on it, because these tubes run at about 200 volt I believe, but the starting process requires a much higher voltage, I think somewhere around 20 kilovolt. And the cathode filament of these tubes is actually quite robust, not just because of the high current, but also because the starting process is actually quite violent from what I've heard. Now, there's also a huge warning sign on this tank on the right, which tells you that basically all of it is on high voltage during operation. So not something you want to touch. I think that was the reservoir tank, basically for to keep the argon pressure quite stable, because argon can be buried into the walls of the tube, and I think a tank like that can keep the argon pressure more stable during the lifetime of the tube. About lifetime, there is an hour counter somewhere on there. Let's see if I can zoom in on that. But the downside is either I don't know how to read it, or it's already past the 5000 hour scale and it's just full. Now at the front is the output coupler mirror, and those adjustments are, well, not really accessible, but I don't think that's something that you'd want to adjust yourself anyway. If the laser runs fine, that's something that shouldn't really need adjustment unless you touch the cavity mirrors. Sometimes lasers like these can even have a tube swap without having to touch the mirrors. Now on the back is the high reflecting mirror and the wavelength selector, and it was on a bit stiff, but I managed to be able to get it off. It's sealed with an O-ring against dust. There's even a bit of dust there, so I should be careful. But I'll take it off very shortly. And inside, see if I can focus. Inside you can see a prism directing the beam to the high reflecting mirror, and the dispersion of that prism makes the cavity stable for only one wavelength. So yeah, that's the inside of the laser head. And these three rods give the cavity its stability, and the laser tube itself is just hanging in there. but it's not responsible for the alignment. One thing that's very neat on this laser is the shutter. If I move it from open to closed, you only see this part moving, but you don't see any actual shutter opening or closing. That's because this is a magnet. The actual shutter is inside the laser tube, inside the cavity. So this both keeps the shutter clean and free of dust, but also inside the cavity, once you block the laser, you don't have to dump all the power. So that's really neat. Here at the front of the laser head, I believe this would be the pick-off where it actually measures the power. Let's draw what's inside the laser head. We have the plasma tube, which has two Brewster angle windows on both ends. And the window at the Brewster angle has pretty much no losses at one of the two polarizations, so it can freely circle light in and out. Now, on one end of the tube we have the cathode filament, on the other end the anode, and the discharge runs between these two. And there's a big magnet around the tube to confine the discharge to the center. Now, why is this needed? Well, an argon ion laser has a laser medium that consists of argon ions. So the laser must create its own lasing medium by ionizing the argon gas. To have a decent laser medium, you need a very high current density to create a lot of argon ions. So the tube actually becomes pretty hot. And there are very few materials that can withstand the hot plasma inside one of these plasma tubes. In my case, I have a bore that's made of beryllium oxide, which is a pretty exotic material. Now, to make a laser, you have to place cavity mirrors around this. So on one end you have the output coupler, and on the other end you could place a high reflecting mirror, and then you have a linear cavity that can output all argon lines, of course depending on the mirrors that you have. Now, in my case, I don't have a cavity like this, but I have a wavelength selector on one end. And that consists of a prism, and the high reflector is placed here. Now, what this does is that the dispersion of the prism makes the cavity stable for only one wavelength. So if we draw the blue line, due to the dispersion of the prism, this is directed towards the high reflecting mirror, and it can bounce back and forth. But if I draw the green line, the dispersion of the prism for green is slightly different, and the cavity alignment will not work. So only one wavelength can lace at the same time. Now what we can do is, this whole assembly sits on the adjusters, so that if you rotate this knob, this whole assembly tilts, and you can select the angle of the prism, and with that angle you can select which wavelength is stable in the cavity, and this way you can select which wavelength you want the laser to work at. Now, outside of the laser tube we have these rods running. The output coupler is also connected to these rods, so that the hot plasma tube doesn't influence the alignment of the cavity. And in here is this shutter that can go up and down, and outside the output coupler we have this pick-off mirror, so that the laser can measure how much power is generated. I got the water cooling hooked up. Let's see if there are any leaks. Well, that's what you get for using cheap garden hoses. So let's give it another try to see if it is watertight. So far so good. Of course, when running a laser like this, laser safety is a very important aspect. The first place to look for what you need in terms of safety is the laser warning label. Now it tells you it's a 2.5 watts CW argon laser, and it's a class 4 laser product. So class 4 means not only the direct radiation and the indirect radiation is dangerous, but also it can set stuff on fire. So it's something to look out for where you point this laser at. It tells you it's CW and it's an argon laser. And you also can find wavelength and wavelength ranges on these warning labels. But in this case, this laser comes in many different configurations, and it's best to look up in the manual what kind of wavelength can come out of your particular laser. Fortunately, many laser safety goggles actually span pretty much the whole range that an argon laser can give. Only very special lines like in the infrared are not always covered. The 2.5 watt rating is of course very optimistic when it comes to the specifications if you want a lot of output power, and it's on the safe side when it comes to laser safety. So the laser itself is rated for a 1 watt output power if you run it multi-line, and with the line selector that I have, I can only get 400 milliwatt out of the brightest line. So you see that there's quite some safety margin, such that if there's a malfunction or you have a particularly hot tube, that you don't exceed the safety rating, which would bring you in a dangerous situation. The 2.5 watts power is roughly in a 1 mm square beam, and that surface area then corresponds to 2.5 megawatts per square meter. And if you look at the EN 207 laser safety standard, it should correspond to a rating of DL6, which is actually pretty high. Now fortunately I have laser safety goggles that are rated that high, but due to the fact that I have this line selector at the back, that already gives me an extra safety margin. I cannot run it multi-line and obtain a higher output power. So I would also be comfortable with laser safety goggles that are only rated for DL5. Now the rating of laser safety goggles is always printed on the goggles itself, and here you see a long list of small text of the rating of the goggles. And these goggles are rated for several wavelength ranges for both pulsed lasers at several pulse lengths, each one with their own rating, so it gets quite a bit of text. Well, this is all calculated for the worst case when you stick your head straight in front of the laser, and due to the divergence, the beam will spread out within a meter to below 1 watt per square millimeter, so with an L5 rating you'll be fine. Okay, here goes. If suddenly the light turns off, something went wrong. Line is okay, fuse 1 is okay, fuse 2 is okay. So far so good. Interlock is not okay. Okay, all interlock issues should be fixed by now. Water is running. Let's see if it works. We have an interlock light, so that should be good. Let's go for power on. It should take about 30 seconds before the ready light comes on, and there it is. Okay, I got it set to maximum current, which is what the manual says. The emission indicator is on. Let's turn it on. Let's see what we can get out. There is a discharge, but no laser. So could be that the resonator is misaligned, because it has an adjustable resonator and I have no clue if those knobs have been turned and if the alignment is still okay or not. I'll just jiggle one of the alignment knobs and bring it back to the center, see if that works. The tiniest bit of light right here. It's super sensitive. So the tube is running, We have lasing. Now let's try not the vertical but the horizontal adjuster. Oh, there you go, wow. Oppa, there we go. I have no clue which line I have selected, but we have a working laser. There we go. My argon laser actually works. This thing has been sitting still for so long, because these lasers don't always like it sitting still, I believe, for a very long time. And very long time is like more than 10 years. I have no clue how long it was sitting still before I got it, so it could be a lot more. But hey, it works. This is awesome. It is buzzing like crazy. I mean, the power supply has this huge transformers in there and it's just one big hum. Now, the regulator voltage is now below 10 volt. I can wire the taps on my transformer slightly different to give it a bit of more overhead, because probably right now it's not very stable. I have the wavelength selector at the back. Let's see if I can change to a different line. Now, if you hear the water running in the background, that's just the sink that doesn't flush properly, so every once in a while it makes a lot of noise. Oh, will you look at this? Look at this. I changed the vertical adjustment, which is in the wavelength direction. I'm now getting violet lines. Ooh, pretty short wavelength. Really short wavelength. Now cycling through it. That's the really bright blue one. And green. See if I can go further into the green. Oh, look at that. Yeah. Oh, this is a bright green line. That was it. This is a very bright laser. Multi-line argon lasers are really fun. You can just, at the turn of a knob, change the wavelength. You get this whole range from violet to green. That's just beautiful. But yeah, this thing runs like it has never been turned off. I now have a power meter in the beam, and I'll cycle through the lines and tweak the alignment for each of them and see how much power I can get out. So this is the bright green line. And the power meter is a bit slow to react. 0.415 watt is actually quite nice. It's specified at 400 milliwatts, this line. I think there's some backlash on there because it doesn't feel completely linear. Now let's cycle through the wavelengths. It's got 46 milliwatts. Okay, that's the second line. Let's go to the next one. 137. $368 milliwatts. Under 30 milliwatts, under 32. A whopping 23 milliwatts. There's even a weaker line right here. 12 milliwatts. Another weak line at 39 milliwatts. And that's the last line. I really enjoyed working on this laser. It's a nice project. It's an old laser, but still it's very interesting to see how things are made. And it is fascinating to have a visible wavelength laser that can change wavelength at the turn of a knob. I think that's yeah, really nice to look at. And of course, with any visible wavelength laser, no video would be complete without a shot in the dark. So thanks for watching, I hope you enjoyed, and I hope to catch you next time.